Hello, my name is Russell Todd and I'm a second-year computer science PhD student at the University of Wyoming. I work in collaboration with the kinesiology department to explore human movement in virtual reality. Temporal availability of Ebbinghaus illusions on perceiving and interacting with 3D objects in a contextual virtual environment. Authors Russell Todd, Jin Zhu, and Amy Banish. The reach to grasp action is a common action in daily living and occupational tasks. This action is governed by planning and control mechanisms based upon perception. In addition, there is the dissociation theory of perception and action. The main gist is that visually guided movements should be largely immune to the perceptually compelling changes in size produced by pictorial illusions, like the Ebbinghaus illusion. The Ebbinghaus illusion is known to affect perception of object size and actions to interact with said object. Thus far, studies have only evaluated the Ebbinghaus illusion using static 2D objects. A recent example of this would be the Finney and Jones paper published last year, which explored the illusion in several different implementations, but all as a 2D representation even if in a 3D setting. A more traditional example of an Ebbinghaus illusion study would be Alfonso et al.'s study of its impact on the Fitz tapping task, which is where a subject rapidly touches between separate points, which was also done in 2D. These limitations helped shape our goals for our own study. For our study goals, it is to use integrated motion tracking and immersive 3D virtual reality technologies to assess perception of 3D object size with the Ebbinghaus illusion in a VR environment. We must also evaluate the action of reaching to grasp a 3D object with static and dynamic Ebbinghaus illusions in a virtual reality environment. But for our study questions, the first is, does the Ebbinghaus illusion persist with 3D objects and impact interaction with 3D objects? Secondly, how would sudden changes to the illusion impact motor control during a reach-to-grasp action? Our original base hypotheses were that we would see the Ebbinghaus illusion continue to have an effect similar to what had been previously observed in the more traditional studies, in that one could positively or negatively impact a subject's performance by making the target appear larger or smaller, respectively, under both static and dynamic illusion conditions. Throughout this video on the Ebbinghaus illusion, there are study terms that will be used that need to be explained. The first is hand visualization. For our study, we have 3 dots that represent the virtual hand. The first is the blue dot, which marks the forefinger sensor. The green dot shows the thumb sensor, and the red dot shows the wrist sensor. Home and target. So first, the home sphere is the red dotted sphere you can see in figure 2. The user starts with their fingers inside this before beginning any reach to grasp action. The target sphere is the orange sphere also in figure 2. It is the focus of the reach to grasp motion. In figure 3, a quick refresher on the Ebbinghaus illusion is shown. The central target is made to appear larger, as in the left example, or smaller, as in the right example, by the inducers. The inducers are the features surrounding the target. In plain terms, those are the white spheres surrounding the orange target sphere. In experiment 1, there's the judgment task, which shows in block 1 as sphere creation, and it includes control, small, and large conditions. Experiment 1 is foundational to experiments 2 and 3. Therefore, we have a visual example of the blocks and conditions used in experiment 1. In the judgment task, the participant is instructed to create a sphere of the same size as the one shown on the left. This is done under control, small inducer, and big inducer conditions. For the reach to grasp tasks, there's block 2, 3, and 4. Moving to the reach to grasp tasks, we have block 2, which includes control, static small inducers, and static big inducers, as you can see in the video shown. In block 3, we have the first dynamic illusions with control, small appear, small disappear, large appear, and large disappear, which you can see here in this video. Control, small appear, small disappear, large appear, and large disappear. Here in block 4, we have our next set of dynamic illusions in which the inducers will swap to the opposite condition. So it includes control, small to large, and large to small conditions. When we finished Experiment 1, we wondered if the participants seeing their virtual hand could be impacting their performance, so we designed Experiment 2. Experiment 2 is a repeat of Experiment 1 blocks 2, 3, and 4, the reach to grasp tasks in particular. It adds in an additional condition for the occlusion of vision of the hand. So there is occluded early, occluded late, and occluded entirely. When vision of the hand is occluded early, the hand is invisible from the moment that the participant's fingers leave the home sphere and until they reach the halfway point. Occluded late is when the hand disappears at the halfway point up until the point that the participant grabs the target, completing the reach to grasp action. Occluded entirely is when the hand is invisible from the moment that the participant's hand leaves the home sphere all the way up to the end of the motion when the participant grabs the target. Experiment 3 was designed to explore how vision of the contextual target affects the reach to grasp action. Therefore, Experiment 3 is with perturbed vision of the target and its surrounding features, which is to say, the contextual target. There are perturbed early and late conditions. For perturbed early, when the participant leaves the home sphere, it triggers the disappearing of the contextual target, while repeating Experiment 1 blocks 2, 3, and 4. Perturbed late is the same, except the trigger for the disappearance of the target and surrounding features occurs at the halfway point. In cases like swapping, where they will see both inducer sets of small and large, it would start on small, and then it would swap to large for a small fraction of a second. So just long enough to flash that image to the participant, and then it would disappear entirely as normal. The Ebbinghaus illusion's effect on perception is that it does strongly affect perceived size of a contextual 3D object in an immersive virtual environment. This suggests that human perception is contextual and susceptible to change of the environment. Now, when we look at the Ebbinghaus illusion effect on action and interaction, in all three experiments, the illusion ceased having an effect on the action to interact with the object. Contextual features, meaning the inducers, only reduced peak and terminal grasp apertures, so the inducers were treated as obstacles, constraining the participants' fingers during their motion to reach to grasp the object. This supports the dissociation theory of perception and action. Now, depth perception was not assessed in the perceptual task, but we did notice that there was a depth perception effect induced by the Ebbinghaus illusion in that participants grasped the object closer to their body. However, the effect on action was only noticeable in dynamic illusion conditions where inducers swapped from large to small, such that it's perceived closer when surrounded by small inducers, but not farther when surrounded by big inducers. This supports the theory suggesting that illusion effects on depth perception are asymmetrical, which is one of the findings of the Finney and Jones paper. Consistent with previous studies, the vision of the virtual hand and contextual target both play a strong role in visually guided interactions with 3D objects in virtual reality. For the vision of the virtual hand's role, sight of the hand is unnecessary in early planning and execution of reaching towards a target, but it is needed for fine-tuning the action in the end, whereas the vision of the contextual target is needed for planning the action in the beginning. Notably, with haptic information absent, more time is needed to form precise grasp apertures through visual detection of the margin between the fingers and the rim of the object. Special thanks to Wyoming Embry and the Wyoming NASA Space Grant Consortium for funding my research. If you have additional questions or comments, you can reach out to us at the email addresses shown. Finally, I would like to thank Dr. Banich and Dr. Zhu for their aid and support in my growth as a researcher. Thank you.